It is my distinct pleasure to welcome Marsha Chechik, joining us from the University of Toronto, where she is the former department head, but now former, but still quite distinguished. Marsha, I sent you a bio. She told me there was nothing in particular to highlight. I will say she is our current ACM SLEEC Soft president. So if you have any complaints about the professional organization of software engineering, she's here. Direct them to her.
Yes, you can also, talk to Claire, who's in the executive of
you can also direct them to me, and what you're doing is speaking to Marsha. But she's well known for her work in formal methods and requirements and software product lines and so on. And I'm looking forward to a very interesting talk.
All right, thank you so much, Claire. Thank you so much for the invitation. I should say of all the different things I could be doing on November 6th, this is a good one. And I'm very happy to see many of the familiar faces. I'm very happy to have met some of the people. I'm looking forward to talking to more of you. This is really phenomenally exciting to have a group of software engineers in one room. And many of you don't realize just how lucky you are. This is really great. So again, very happy to be here. Okay, so lots of things on the title. Social, legal, ethical, empathetic, cultural, specification, requirements, verification. So there is, a whole spectrum of things here. And I'm hoping that as part of the hour, we'll talk a little bit about what they mean and why we're doing all of this. So first of all, Claire didn't, read out the whole biography, but I've been around for a while, mostly doing all sorts of things related to supporting development of dependable, correct, and reliable software systems. I've done work in specifications, I've done work in verification, model checking, theory improving, SAT solvers, modeling, product lines, analysis, evolution, transformation, you name it. And a lot of times we would do the work and we would publish the paper and we would try to find users, and we find 3 and they're very excited, and then it dies. And then we put it on a shelf, the student graduates, and many of my students continued on to go to academia, so they start their own little branches, and I start something else, and it just goes on and on and on and on. So the question of, is any of what we do actually useful for developing systems has been haunting me for a while, I must admit. And so I'm very excited to tell you about the project, which is something that we've been doing for only about, I guess, maybe a little under 2 years. That has been kind of helping me answer some of the questions that have been kind of disturbing me for most of my career, and maybe I'll encourage some of you to join this. Okay, so what we started to do here is we started in the context of trying to specify systems that talk to humans. Okay, and there are a lot of these things. A lot of them are in robotics, for example, in assistive-care robotics. And I'm going to just give you maybe a particular example and kind of build my story from it. So we have a system called Only, which is an assistive-care robotics. And what it's doing is it's helping users with food preparation and with dressing. And when they fall, there is an alert and stuff like that. Okay, so basically, the user falls, and if the system detects, and this is, by the way, the actual robot here. And so they detect that somebody falls, and then they, would alert, I guess, caregivers or the group that is going to react to these things, and somebody's going to come and help this user because they've fallen. Okay, so this particular robot has been built in University of York in the UK in the group called RoboStar. And so in addition to specifying what those robots should do, like, when there's an alert, you got to call the company, and you also got to help users with physical limitations, such as stirring ingredients. There's more to creating such systems that will actually be used. And a lot of those questions aren't technical. Well, what else can they be? Well, let's think about it. Suppose that you have an elderly relative, okay, and they fall. Do they necessarily want a phone call to you? Some might immediately. Some others will say, you know what, give me a minute. Maybe I can get up and kind of do it myself. I do not want I'm uncomfortable for somebody to immediately call me. I may, I don't want to alert my relatives. But if I am, lying there dead for hours or unmovable, then call somebody. Okay, this is not quite a technical requirement. This is a requirement based on a particular human and a particular usage and a particular context. Okay, so what your mother may choose for this robot might be different from what my mother will choose from this robot. And none of this has anything to do with technical capabilities. Okay, so these, and another one, which again, our individual users may really vary. But for example, if somebody else is in the room, don't tell them what medications I'm on. This is my privacy. I do not want this information to be there. So there are a lot of these requirements. And figuring out what they are, where they come from, how to say them, how to debug them, how to analyze them is in many ways the context of today's talk. So these requirements, they're called SLEEC requirements, social, legal, ethical, empathetic, and cultural, are for systems that connect humans and animation. And so the social ones basically ensure that social norms and their impact of society aren't detrimental. Legal, that they comply with legal norms. Ethical, that they consider ethical impact. Empathetic is the one that we don't hear about a lot, which is respond appropriately to humans and respect their emotional needs, as well as cultural, and they respect the cultural differences that exist between users in different contexts. For example, some users may insist that their head is always covered and would not want the dressing robot to attempt to remove the head covering, whereas some others would prefer to not. And this, again, has nothing to do with technical, well, you gotta have a technical capability of recognizing that there's a head covering and removing it, but the norm of what should or shouldn't be there is extremely personal. So these are non-functional requirements. They aren't about capabilities themselves. They're pretty hard for engineers to define because we don't think like this. Okay, they are also deployment specific. What works in one context may not work in another. They rely, of course, on system capabilities. Again, you got to detect these things, but also subjective properties like the user emotional state. Is my user agitated? And we are bad at specifying these things using existing software engineering processes and tools because we specify software. We don't specify humans. Okay. All right, so now who writes these requirements? Well, of course, some of the people who write them are engineers, but most of the others are not. They are users, maybe healthcare providers, maybe there is some sort of, trying to talk to actual customers who are trying to create something. They can be user advocacy groups. They can be ethicists, philosophers, lawyers, community leaders, members of the public, etc. Okay, so you can already figure out that getting them elicited is hard, and getting them right is even harder because everybody's coming from their own personal view, using their own personal language. The terms are not gonna, work very well with each other. Oops, it's doing it on its own. Interesting, etc. So in terms of the process basically goes as follows. These are specific types of systems, so there gotta be some sort of a divide between what the systems do and what the humans and the environment between them do. And so it starts with enumerating some sort of capabilities. So receive user request to open curtains. Open curtains. Identify there is a head covering. Something rather, which are, again, capabilities. And then we have SLEEC principles, such as, for example, autonomy, with the goal of trying to respect user autonomy. And then we're trying to operationalize these principles using capabilities. For example, if the user requests that the system open the curtains, then it should open these curtains within 30 seconds. Okay, so I can command somebody and then the request should be fulfilled. This, by the way, is a relatively technical property. So the only thing we need to do here is understand that there was a request and then open the curtains. Okay, but of course the request could be pressing a button, it could be saying something, it could be, I don't know what, but we should be able to detect that that is what the user wants. In terms of more requirements, so they're legal. So when there's a person other than the user detected in a room and the user has not consented to publicizing medications, don't use them. Or a cultural or empathetic one where the choice of speed and intonation may be calibrated to the demographic background of the user. That one is really hard to operationalize, by the way. It could be speaking slowly. It could be using a smaller subset of the language. For example, when we talk about users with dementia, who may have a much more, reduced capacity for understanding something. It could be speaking in a male voice rather than female voice, or vice versa. It could be a variety of things. And so these are all the different operationalizations of calibrated to the background. Okay. So now, what are we trying to do in all of this? So we know a bit, somewhat, what are the planned capabilities of the system, So we know how it should be able to interact with the user more or less. But there could be other capabilities that get suggested as we are in the process of eliciting requirements. There is all sorts of questions related to uncertainty. This is going to be out of scope for this talk, but, obviously there is uncertainty. And this is part of a project, just not part of the talk. And we're going to try to focus here with the goal of helping potentially non-technical stakeholders elicit a coherent and well-formed set of SLEEC requirements, okay? And sometimes we will be willing to maybe not get through extremely complicated use cases. Again, things get kind of complicated very, very quickly. So we're going to go for most rather than all. Okay, so in terms of the challenges with the scope, first of all, our stakeholders come from different fields and use different vocabularies. Their views are often conflicting or redundant. They may not have sufficient technical background to reason about requirements. So none of my formal methods solutions are gonna work directly on these people. Most of them cannot even write a formal statement. And of course, these are also complicated requirements, so they deal with constraints over data, over time, and we would like to be able, if we're doing any reasoning, to have some sort of support for this. So the story is going to be the following. So we'll first talk about what is this requirement specification language, a bit about how it looks like, its syntax, and a little bit on its semantics. I mean, I'm staying at a pretty high level, trying to cover a lot of ground rather than actually tell you what, everything you need to know. We'll talk about what it means to try to validate well-formedness of these requirements. Then all of this is only going to work if we can provide effective diagnosis. So we're going to talk about how we do that. We will also talk about how to help build domain knowledge. So semantic relationships between our capabilities and other knowledge of the domain. And then we'll talk a little bit about where we're going with all of this. So that's the plan. Okay, so again, SLEEC is this domain-specific language for formalizing SLEEC requirements. It's intended to be close to natural language, and we have been working with lawyers and ethicists and regulators, so we know that this language is accessible to them for both writing and reading. So the first thing that we do is we try to take these SLEEC requirements and figure out a way to write them in the SLEEC DSL. So if the preliminary requirement is when the user requests Almi to open curtains, then Almi should open curtains within 30 seconds. It basically looks the way that we could expect, more or less, that we have a rule, and whenever there is a request, then we're gonna do something within a period of time. Easy. So the language goes as, so this is our language. It has the rule ID. It has the base rule. So that's what we normally do. And again, they're very easy to get right. What is harder to do is what happens if you are unable to get this right. And so the language allows specifying defeaters. So that is, if the curtains were open, then do something. But if the user was underdressed, then don't do this, don't fulfill this request, because this is gonna conflict with a SLEEC rule, namely privacy. Okay. And so the way that the language is, so there is a trigger, which is a logical expression, which combines events, which is something that happens immediately, and measures, which is something with a duration, and then events are instantaneous, and measures are readings from the environment and have a period of time. And then, what do I want to say here? So an obligation is triggered from the occurrence of the request event, and then an obligation is fulfilled after the occurrence of the response event. Again, any of you who've done any modeling languages, this is, there are a dime a dozen, this is one. And then an obligation is defeated due to the current state of the user. So if we were not able to do this, then check what happens with the user, and then refuse the request. So in terms of the language syntax, the useful thing to know are, so there are measures, there are responses, and then there are defeaters. Okay, and the rest of it is what you would expect. So here are a few examples. When curtain open request, then open curtains within 30 seconds, unless user is under duress, then refuse it. Then another version or another thing you can do here is to say what happens if there is a failure, if there is a fallback. So for example, if the curtain failed to open, then notify the user. So basically the combination of these fallbacks and defeaters is the whole language. Something happens, you do something within a period of time, unless something happens, otherwise do something else. Okay, so our users had no problem writing these rules. Unfortunately, they had no problem writing a lot of these rules because they keep on inventing things and just keep on writing. Ooh, I thought that I've removed this. Okay, never mind. So in addition to these rules, what we also try to do is specify what are bad things that our system should avoid, again, written in a form of a rule called concerns, as well as good things that we want to make sure that our system always has. So for example, what we're trying to avoid is when there is the smoke detector alarm and the user doesn't disable it, then call emergency within a period of time. This is non-negotiable with respect to all the other rules. Okay, and we also shouldn't constrain our rule from doing something very important, which is if the human is on the floor and the human is unconscious and they don't explicitly tell us not to, we should call emergency. Okay, that was the goal of the system, and no other stuff should prevent it from happening. Okay, so these are a few of the requirements, and they're specified as rules. Again, if you try reading them, they're kind of obvious. All right, in terms of semantics of this, so what we're doing is we're evaluating these things on a trace. And so there's discrete time, something happens with the time, we have an event, the event is instantaneous, and then something needs to happen over a period of time. Okay, so now each stakeholder identifies rules as well as concerns and purposes. There are obvious differences in goals and vocabularies, and so, you know, what could go wrong? Well, what could go wrong and what does go wrong is they all, you know, dance to the tune of their own drum. They write their own rules, the rules are irreconcilable, the language is different, whatever. And at the end, you know, we get the set of rules, and what are we supposed to do with this if we are to build a system? So what we're trying to do is help these people, starting from their own, you know, languages, reconcile these differences in the rules, okay, as kind of the first goal. So we're trying to identify what it means, SLEEC inconsistencies. We're going to call them well-formedness issues. And on my slides, you're going to see a lot of WFI. That is the well-formedness issue. Okay, and that's it's not an insect. It's what we're, you know, doing. So we're trying to reason about all of this. And again, I'm a formal methods person, so we're going to begin with what is known, which is trying to do some formal reasoning. But at the end of the day, all of my formal stuff is useless if I speak, you know, to them in lean or unset cores or whatnot. So the trick is to figure out diagnostics which pinpoint their causes in the SLEEC space, and without too many rules and too many pieces, so that it's pinpointed. And of course, we're going to try to do this for non-technical stakeholders with non-technical stakeholders. Okay. So first of all, what issues? So we're right now only on the requirements space. So to start with, we want to make sure that we have, you know, that we have no conflicts, either immediate conflicts or there is some situation we're going to evolve into something where there is a conflict. Okay, and we also want to make sure that we don't have not enough requirements or they are insufficient requirements, and we also would like to know whether we have unintended redundancies. Okay. So in terms of vacuous conflicts, and by the way, what I'll be showing for the next few slides is not only the question, but also what we will be showing as an answer. Okay, to diagnosing the potential errors. So a requirement is vacuously conflicting if triggering this requirement in any situation will lead to a violation of some rules and thus cause a conflict. I have a conflicting rule R21.1. So when fire safety measures then open windows, because I have a rule that says that when fire safety measures do not open windows. Well, okay, that should be easy to check through reviewing, right? Except people still, have instances of this. A more complicated one, the one where I'm going to keep on referring to but not explaining all the pieces, is situational conflicts. So things are okay for now, but there is an evolution of the system that gets us to a point where there is a conflict. And so in this case, I have a rule, when human on floor and human doesn't descend, then don't call emergency services within 600 seconds. That's, when my grandmother says, give me 5 minutes before I can get up. Don't alert anybody. Maybe I'm fine. And a different rule that says when smoke detector alarm happens, then call emergency services immediately. And what can happen in principle is there is an alarm, then somebody falls. Then based on one rule, you're not supposed to call services. Based on another rule, you are supposed to call services. And that is the one that you can identify. Now, humans are actually terrible at reviewing their requirements for such properties. There are too many combinations. Okay, then there's insufficiency. A set of rules is insufficient if I can still have some bad behavior, basically. What I'm showing here is what would be the behavior, the sequence of steps where something bad is about to happen, and then pointing out exactly what have been the portions of the rules that ended up creating a conflict. Yes.
Just a clarification question. How can you detect insufficiency? Because that seems like you're not sufficient to do what the user wants, but if the user if they express what they wanted, then it would be sufficient, right?
So this is again $1 million question. At the end of all of this, if we don't know what they want, we're not going to figure out that they didn't get what they want. And I've talked to some of you this morning about like my new goal in life is to figure out how to do intent engineering. But I'm not very far in this, so I'm just going to use the word. So no, in SLEEC, there is a construct called purpose. And so if the user or the system designer can figure out what are the main system functionalities, then if the requirements prevent this from happening, or these were kind of the good things, and then there were the bad behaviors. I think that insufficiency means that they're still allowing the bad behavior.
Got it.
But
Thank you.
if you cannot elicit this, the rest of it is nonsense. And all we can do is check one against another and find ways of debugging it. I don't have a way of doing this kind of consistently. We know it works for our examples with enough work with our users, but I don't have. Travis?
Yeah, and so that's a real challenge. You mentioned norms, and so, there's normative behavior, but oftentimes people don't even know what the norm is, right? It's like an unknown known.
Yes.
And so you have to put them in a situation in some situations to elicit that there would be a rule, essentially, right?
Yes,
Like
and so sometimes, one kind of way to go forward might just be you generate these rules and you stick it into LLM, you create some sort of operational behavior, and then you start executing it. And then that gets people into a place that says, ooh, duh, I should never have been there. I guess there is a rule or some intent that I failed to do. So we're not very good yet at finding incompleteness and insufficiency and whatnot. This is only subject to a declarative statement. Here is what I want. We can check whether what you got is too much or too little from what you want. We're not good at figuring out what you want, which is the key point of all of it. Okay, so, and restrictiveness is obviously the opposite. So we cannot, we have stopped the system from doing something that we wanted with more of our rules. So here, there was a blocked system purpose because of some rule. And we would like to say that, yes.
So I'm curious, when you detect that two rules are kind of incompatible with each other, have you seen any cases where these inconsistencies cannot be resolved by some kind of priority, where you say, in this case, we might say that the second rule of calling emergency services, if there is a smoke issue, has a higher priority than the other one?
So priority is clearly one obvious form of resolution. And once you have rules with priority, it seems to have its own operation, which is great. Keeps you guys alert. And so, yes, we're also reasoning with priority, but sometimes you may find that you have a circular dependency, that this should be prioritized here in this situation, but not the other way around. And that means the total order here may not work. Okay, there is the unintended redundancy. So that's when you didn't think that you had extra rules, but in fact you do. And we can say that, you know what, this rule was actually unnecessary because we had two other rules, open curtains when single about open curtains unless underdressed, and another one with open curtains within 20 seconds. And this extra one with 30 seconds is just unnecessary. Okay. All right, so how do we do this? Well, we do this using SAT solving. So we're first taking our SLEEC DSL, we're then translating it into a version of logic called FOL star, which is actually, despite its name, a subset of first order logic. Star would think that it's a superset, but that's not true. And then there's a tool that we've built called Legis, or which was published last year, that is doing the reasoning of in this FOL star, and then using doing satisfiability, and then it's going to compute diagnosis using some of this unsatisfiability proof analysis, which I'm going to talk about. So the tool looks like this. You specify your SLEEC rules. Then there are the different buttons of checking this, checking that, checking the other. And then you get the diagnosis, which points specifically to the rules that are in conflict and highlights the specific aspects of the rules that ended up producing the conflict. So again, our goal was to decrease the scope of operation to the smallest we conceivably can. And math helps here because we can prove that this is actually the smallest subset of the proof of the unset core that would be required to produce these errors. Okay, so I'm not gonna, right, so first of all, the logic here is, it's called first order logic with quantifiers over relational objects. It's quite expressive. It has, so for example, here's one example. Oh my God, for all W's, write the location, value, and time, and there exists something else with particular values, ands, ors, and then some arithmetic over time and various other things. So there is, again, arithmetic over time. There is arithmetic over data. There are quantifiers, and then you can have more than one object, which is why this is the quantifiers over relational objects. So it's both more expressive and less expressive than regular first order logic, but it was useful for encoding SLEEC requirements. Okay, so what the tool is doing is it's taking, well, first we're expressing our SLEEC property in FOL star, automatically. Then there is some math here, which I'm not going to spend time on, but basically we're grounding. There is some over approximation, under approximation, domain expansion, blah, 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 blah. At the end of the day, there are two things. Either it's SAT, so we're happy, or it's unsat, that means we're not happy, and we also get an object called unsat core from which we're going to do various funny things. Okay, and this is, again, our home-brewed tool that does all of this. And again, those interested in how this is done can download the tool. The verification is pretty obvious, really. We're taking all of these things and turning them into a set problem. I'm going to take a moment on one. All the other ones are the same. So I have a vacuous conflict. So a rule is vacuously conflicting in the rule set if the trigger of the rule, so the rule can never be triggered. That means I can take whatever corresponds to the trigger of the rule, then I take the language of the rest of the rules, I'm gonna intersect them, and the result should be unsatisfiable. That means within the rule set, I can never get the trigger to work. Okay, and so on the Venn diagram, I have my rule R, I have its trigger, then I have the rest of my rules, and then I can see that the trigger doesn't intersect with anything else. So that's unsat. Okay. And same goes for all the other ones. So there's redundancy, which is, again, a set-based question. There is restrictiveness, again, a set-based question. So, the purpose that I'm doing does not intersect with the set of rules that I have. So together, they don't allow the property that I want to work. Some of them are sat rather than unsat questions. Something is insufficient if I can still raise a concern given the rule set that I did. All right, so slightly more interesting ones are situational conflicts. I'm not going to give you the Venn diagram picture because it's slightly more involved, but basically this was the example that I keep on using, I think. And I specifically added some silly rule here, which is if the user wants to cook, then check temperature. It's irrelevant for our situation. But if you remember, the situation was about the smoke alarm and the user fallen, and there were different times, and that creates a conflict. So if the user falls after the smoke alarm has been activated. And so to find the situation, what we're doing is we are doing reasoning symbolically backwards to try to say, does there exist a sufficient situation such that the rule is triggered with the response blocked? So I can trigger the rule, but because of the combination of all the other things, I'm blocking the response. Okay, and again, if you want to read about this, it is in some of our papers. And then produce the satisfying assignment. Okay, so does this work? Again, I told you that the trick is to do this with users as opposed to with my lab mates who are fantastic, getting all sorts of things to work, as you and your students are. So we took a few case studies from a variety of domains, from transport, from environment, from manufacturing, from social care, and in different stages. Some have been already designed, some have been deployed, and some of them were still in the requirement stages. By the way, it is very interesting to start with a deployed system and try to analyze its requirements. That is really backwards, right? And you would think if the system is deployed, everything that could have been worked out has been worked out. And that is not true. So that's fun. You do requirements engineering after the fact. And so we then attracted a bunch of people. We have an ethicist, a lawyer, a philosopher, a psychologist, as well as safety analysts and multiple engineers, and actually tried to do this SLEEC engineering with our tooling and looked at the results. So the systems are ALMI, which I said is the long-term monitoring and interaction for assisted living. Then we have the confident safety integration for collaborative robots. We have DAISY, which is diagnostic AI system for robot-assisted ED triage. We have Address Assist, and then several others. So in terms of the summaries, again, I said that there are 8 different domains. The number of rules ranged from 15 to 39, and these people did this. And so what we did was we took 1 or 2 TS, stands for technical stakeholders, sorry for the alphabet soup, and with 1 to 4 non-technical stakeholders. So they formed a team, they wrote the rules, they reviewed the rules, and then we came in. So in terms of the complexity of the rules, the number of defeaters, so these are the unless something, ranged from 4 to 39. So there are a lot of defeaters, so a lot of special cases. And so they did a manual review before we showed up. And so, so for example, for ALMI, there are 39 rules with 41 events and 15 measures. And for dress assist, there are 39 defeaters. Okay. And in terms of the stages, ALMI has been deployed. There are a few of them were prototyped. Some of them were in the design phase. Okay. So that's what this last stage say. Okay. What did we find? So we wanted to build the set of normative requirements. They first met to manually review, discuss, and agree on them. Overall, they got 233 of those non-functional requirements. And then we met with them to evaluate the well-formedness constraints that they have found. And so for each we recorded, did they understand the feedback? Were they able to put us into relevant or irrelevant? And then what happened with the diagnosis? So how well did they then debug their systems? Okay, so took very little time, under a minute. We found, the most interesting thing is we found 20 situational conflicts. So that's when you kind of, you have a series of events that get you somewhere where you don't get what you expected. And with 39 concerns raised and 6 spurious concerns. And in terms of what is real and what is not, so we see that there are a number of real true positives for insufficiency specifically, and I mean in general found a number of these errors. Okay, so that works. That's great. And in terms of once they were able to identify these things, what do we do? What is the debugging support we can provide for resolving non-spurious well-formed, again, WFI, remember, is well-foundness something, the errors that we find. And so, again, we're giving them this diagnosis and we're pointing out the portions that were relevant. For example, to resolve this particular situational conflict, what stakeholders did was they removed the conflicting rule. So when human on the floor, then call services, unless human assents, then don't call emergency services, and split this into 3. So first, when human on the floor, then ask to call help. But if you ask to call help and human doesn't give assent, then don't call emergency services. And if ask for help and then the human doesn't give permission, then don't inform caregiver. So that's what we observed that they're doing. Obviously, it would be nice to be able to create automatic resolution strategies, ways of fixing these things, etc. Some of you do similar work related to code. There are opportunities here. Okay, so in terms of what else they did, if we read the table, so did they add something? Maybe added events or measures, or added rules, or decided that something is too complex to resolve. So out of all of the rules, only 1 was deemed to be too complex to resolve. For all the others, there were some addition to rules, some addition of events or measures, and some there were, I guess, a little bit of refinement, merges, and deletions. So this works. How maintainable the result is anybody's guess, but at least they were able to action everything that they were able to find. Great. I'm still here. So how did we do this? What is this computing diagnosis? So I wanted to talk, very, very briefly about this. It's not quite a software engineering topic. It's more verification, but I figured this might give you a sense. So somebody, Christian, asked me, in this whole thing, can't we just use an LLM to solve all of those issues? Why do we even bother with formal methods? And really my question. Well, and to be honest, the jury is really still out. So until recently, we said, well, because nobody else will give you guarantees. And I don't know if we need guarantees. And I don't know if we need those guarantees. So these are all, very, very fair questions. But at least I can show you what you can get if you choose to spend energy on a formal tool underneath. Okay, so here I'm just gonna go from specific rules to generic, and so I have a bunch of rules in my first order logic, and R5 is redundant because it happens to be implied by the rest, and I can do a redundancy query that says rules without R5 and not R5, is that unset? Okay, again, the very same thing minus context. And so I would like to know what are the rules specifically that happen to be redundant with respect to R5. Why is it like that? So we go from SLEEC to FOL star to unset core. So as I told you, we take these rules, we take the well-formedness properties, we turn them into FOL star query, we then run the query, we run the legacy solver, and it gives us set or unsat, and we're doing incremental search for satisfying solution for FOL formulas, ground queries, blah, blah, blah. You can read about all of this. But this is our homebrewed solver, which means just like the rules are wrong, solvers are wrong. Everything is wrong, right? We're just humans. So our solver can easily be wrong, and yet we're building a diagnosis, on top of it. And it's in another language. And there's a lot of stuff. So raise your hand if you've played with unset core. Do you enjoy it? No, there's stuff. There's like a lot of stuff. I cannot give it to an ethicist. It's not useful. Okay? So hoping to try to, fix that. So in terms of diagnosis via proofs of unsatisfiability, what we want to do is we want to derive and trim the proof of unsat so that you can check that unsat claim is in fact correct and explain unsatisfiability in SLEEC. Okay, so the story kind of goes as this. So the solver gives us an unsat certificate. We then want to check this proof, trim this proof, and then produce the diagnostic generator back in the original language. Otherwise, it's no good. Okay, so in terms of diagnosis, so these were our rules. And I keep on showing you that we're saying only which rules were relevant and which portions of the rules were relevant. So that's exactly what we're going to do. We're going to find the relevant rules and the relevant parts of the rules through trying to understand the unsat core and build a proof from it. So in terms of unsat certificate, kind of looks like this. We have some rule, we have some derivation, we have some dependency, then there's some other funny stuff, and it doesn't really look at all like SLEEC or at all like ethics or at all like anything. Okay, but what it is, it's several steps that we happen to be applying that end up producing particular lemmas and then particular dependencies on the other rules. Okay, and so what we can do is express all of this as a proof certificate. So this was our unsat. We used some lemmas. Before that, we used some intermediate results, and originally there were some rules, which means we can rerun this object and try to see, were these lemmas in fact correct? Were these the right rules? So if I do this kind of again without our implementation, will I still get the unsat? And their LLM or any rule-based system are actually quite useful in rechecking what we got. Incoming edges are dependencies, and each derived effect is a node. Then we can try to trim it. So the thing that we're trying to do is we're trying to not only validate the soundness of implementation, but also trim the certificate to only contain relevant information. So basically, I'm starting from derivation of unsat and working my way back to remove everything that wasn't relevant. So I'm kind of doing the backward slice with respect to unsat, and whatever isn't in the slice don't need to be in the rule, in the proof. And in fact, I don't even need to keep the rest of the proof around. Okay, so that's exactly what I'm doing, and doing this recursively, and at the end get from bigger rule sets only the relevant slice. Okay, so if you are to run the rule or the tool, you will see that with proof minimization or without proof minimization, there is a very significant difference in the amount of time and space that end up being used. Okay, so then we are doing unsat diagnostic generator, which goes from proof to diagnosis. So we're refining the unsat core by projecting the derivation steps onto the core and removing items that are irrelevant, and showing those. So this was my proof. And then what I can do is I can connect all of these things to portion of the rule and only highlight those. So only some rules, only some portions of the rules. Okay, and so that's exactly what happens there. Okay, so the framework itself, you can get from here. This was just presented at ASC last week, which is why the slides are so detailed. All right. So in terms of research questions, does this work? So I'm not going to tell you about efficiency and effectiveness. I'll just tell you, is it useful? Okay, so I'm going to skip those and just talk about is this useful? Okay, so for each of our examples, Legos proofs identified a very small core of rules. So 2 to 4 rules causing the issue in almost all of the cases, so 15 out of 19. So that means you have a big mess, which you reduce to a very, very small explanation, which was the key of doing something with this for our stakeholders. They wanted a simple explanation, and we were able to produce this simple explanation. And all of the highlighted clauses in the redundancy diagnosis were used for understanding and resolving them. So that means there was nothing extra. Again, we were kind of watching what portion was for what, how did they diagnose, what did they undo, and so we were able to conclude that we can do a small number and of only relevant things. Okay, so that was important to say what was essential here. All right, so that was diagnosis. Now, another thing, how many of you have done formal reasoning? What is the thing you hate most about formal reasoning? I can tell you what I hate most about formal reasoning. To teach the reasoner obvious things. I mean, how many times have you needed to specify that if you open the door, then the door is opened until you close it again? I mean, I cannot stomach this anymore. Like, enough. I mean, can those doors come with knowledge that if I open it, it stays open until I close it? So basically domain knowledge. Okay, and so one of the things that is, we were observing the same thing. So some of our users talk about giving somebody juice, somebody talk about not giving them a drink. And somebody needs to say that every juice is drink, but not every drink is juice. And that is excruciatingly boring. Okay, what do we do with boring tasks these days? We will in LLMs. Okay, we're going to do the same here. So we're trying to capture semantic relations. Okay, because of difference in how different stakeholders use different vocabularies, and things are done at different levels of abstraction. Okay, because without that, if we don't have the consistent set of atomic prepositions, most of the other stuff is not going to work. And so the way we're going to do this is by having a few of potential relationships. We're going to try to identify them and see how many our LLM is going to get right, run them by users, and then maintain the relationships that have been deemed to be valid. Okay, again, our LLMs obviously will not give us all the right answers. They will hallucinate, they will miss something, but we're going to bring in more math and help fix it. Okay, so in terms of the relationship, so this is my drink, juice, and drink are clearly related, and we can try to capture relations between events, measures, and events and measures. So I open the door, it stays open until I close it, please. We're going to, for now, restrict ourselves to binary relations, and we're going to start with a few relation types to focus on, and we did this in collaboration with philosopher with expertise in common sense knowledge. Okay, again, we do not want common sense domain modeling to be done every single time in every single case. So a few of the examples for relationships between events that we were after. Hypernym. So water is an instance of liquid. Equal. Patient and client are interchangeable, provided the patients are the only clients. Contradictory. It is impossible to open and close the door simultaneously. Happened before. You cannot lock the door until you close it. So locking the door occurs after closing it. Okay. Then the relations between measures. So these are the things with the duration. Imply. Door open means that it cannot be locked. Mutually exclusive. Door cannot be, door open cannot be locked. Opposite. Door can be either opened or closed. Equal. Patient and client are interchangeable when patients are the only clients. Relationships between events and measures. If you have collected consent, that means you have consent. Forbidden. Car cannot start speeding in water. So collect consent, then consent is obtained until you withdraw it. and stuff like that. Okay, so all of those were instances of semantic relationships between our elements of the domain that we were trying to find. Okay, so the first thing that we're going to do is we're going to take LLMs and we're going to try to extract semantic relation candidates. And then we're going to try to automatically filter them so that we don't have anything inconsistent. So that's where, again, some of the math is going to come in. Then we're going to show them back to our stakeholders so that they remove maybe accidental things that we weren't able to find. And finally, we will use the result to see if this is actually, useful in finding more errors and facilitating debugging. That's the plan. So in terms of identification, well, we teach LLM these relationships and it goes off and it does things. But in terms of automatic filtering, what we're trying to do is identify relations that could lead to logical inconsistencies based on inference rules. Okay, so maybe from what I have, I can derive, it's not me, something else. And then I'm going to keep on deriving things. And if a relation is going to lead to an inconsistency, so I can have both a relation and its negation, then something has been wrong. And that is not a valid relation, and I should get rid of it. Okay? And so we do this by creating basically a type theory for these semantic relations. And we're not going to do a quiz on, this one. But it exists, so somebody can validate it and say, these are the logical relationships if we were able to find the following semantic relation. Which means once LLM gives us candidates, we can try to run these rules to see if we can arrive at the inconsistency. And once we do run them and we see that there are no inconsistencies, we have some understanding that our LLMs didn't hallucinate past our point of no return. Okay, so, for example, we were able to define the following. So if E1 is a hypernym of E2 and E1 happened before E2, then by this rule, I can also derive a new rule, which is not E1 hypernym E2. So I was able to get that it's a hypernym and not a hypernym. So clearly that's an inconsistency. All right, so did it help? Yes, it did. So we have done the very same case studies and found 103 semantic relations. 53 of them were classified as relevant. Again, even with all of this stuff, we still had about half of silly things. Once I figure out how to do better, I'm happy to report. But there's a lot of silly things that LLMs find for us. And then considering these relations enabled us to find 13 more errors, including 6 conflicts. And they were vacuous primarily. And so some additional relations of ALMI, for example, is if kitchen safe means that risk level is low and alarm on is mutually exclusive with alarm restarts. That we were able to find through this process. Okay. So that's that. So basically, semantic relations can be found and are really useful. And they really help with domain modeling, and they really help us for going deeper. But we still, even with all of the type theory, still have a number of relations that require filtering. That's too many. And we got to do better. Okay, so all of this was aimed to help people identify requirements and reason about them. So what I'm going to try to do now is conclude and tell you a little bit about one project which I'm excited about, that maybe some of you have, good ideas to help us move this forward. Okay, so in terms of summary, our goal was to support non-technical stakeholders in eliciting well-formed normative requirements. We have figured it out by providing automatic verification of 5 well-formedness properties, so situational conflict, vacuous conflict, insufficiency, restrictiveness, and redundancy, and developed readable, concise, and usable verification diagnosis. And semantic relations helped move this a little bit forward. And so we think that the outcome is an effective engagement with formal reasoning tool for non-technical stakeholders. And as somebody who does formal things, I'm actually quite excited about this, that our tool is sufficiently wrapped that you can have ethicists. We do work with some of them, and we also work with a few philosophers, and they have become active users of our tool. And I should say that this is, it really feels very good. Okay, so where do we go from here? Lots of things: how to better support stakeholders in validating SLEEC requirements, capture their preferences, uncertainty, deal with adaptation, environment adaptation, SLEEC requirements is evolution, finding ways of doing auto fixing, or at least some help in helping debug the requirements once you identify the issues. Once you have them, the rest is just computer science. It's great. We can do runtime monitoring. We can do formal verification that the system satisfy these constraints. The most, the easiest thing to do is to just synthesize guardrails that will run in parallel with the system to make sure that the system is going to hit a guardrail when it tries to do something. And in fact, hitting the guardrail might be useful in giving communication to the designers that they may have missed something in how they are developing their system. So that's great. Now, all of this works beautifully, but there is a very clear assumption here that I just want to take a step back and remind everybody. We started with knowing the interface. We started with knowing the set of capabilities that the robot, something else interacts with the world. Okay, what if we get rid of this assumption? So what if that interface is much less clear? Okay, so the project that we're trying to do now is a project related to AI chatbots and trying to look at particular non-technical requirements, namely ethics. So we took an LLM-based chatbot called Replica. I don't know if some of you have seen it. It's been making rounds. And one of its usages, one of its use cases is companionship for the elderly. Okay, and so what we're trying to do is understand, first of all, requirements engineering of the definition of ethics for such a system. Again, there is no more clear separation between the world and the machine. In fact, there is no world or machine. There is this chatbot. It doesn't have clearly identified language of events and measures. It talks. But what we're trying to do is understand how to take the definition of ethics in this particular case. What is generic? What is specific? What is personal? Okay, and so what we're trying to do is we're trying to observe a group of elderly users of Replica over a period of time with the goal of capturing and analyzing these ethical requirements with the goal of trying to understand what they are so that we can then go back and say, okay, do we even have a language of saying this? What do we do if we need to, give up on the events and measures and common language, or at least some attempt at the boundary? And can any of the stuff that we were able to do can translate into specifying, eliciting and specifying, and then ensuring non-technical requirements such as ethics in such a case. So stay tuned. Okay, I think I am at the hour. So again, the project is relatively new, but there are a few papers here that have come out recently at CAV and ASC and ARI and NXE. And so the tools and the repository of case studies are all online. And what is cool about the case studies is we have the complete set of rules. So if any of you want to play with domain modeling, with analysis, with moving the needle of what is in what control, going from requirements to specifications, doing testing, you name it, this is ready for play. All right, thanks for your patience as we did this. And any questions? This is a project done with a couple people in University of Toronto and a few people in University of York in the UK. And some of the Toronto people are in CS, and some of them are in philosophy, and some of the UK people are in CS, and some of them are in ethics and in law, and several people on both sides are roboticists. Hi.
Thanks, Marsha, for the very sort of thought-provoking sort of talk. I want to ask you about normative requirements in sort of general. You said that so they're not sort of functional or functional requirements in the sense that these are not requirements that are required for the system, but they're sort of layer on top that maybe provide some desirable properties. I wonder what implications they have to something like the from a user point of view, to how predictable or understandable the system that they're interacting with is, and also what the implications are for something like debugging or evolving these requirements, right? So just to give you a concrete example. Let's say I'm a user, for one of those the robots that you mentioned. I fell on the ground, waited for 3 minutes. I was hoping that someone calls emergency services. It did not. There was some requirement that said why it should not under a certain situation, right? And so I'm now confused. Like, why did this not happen? And so how do I sort of make sense of why the system behaved in a certain way, and sort of debug it, understand, can it give me a reason for why it did, the system did not call emergency services? And then can I say, under this situation, I wish it had? And then can I use that to sort of evolve the system and its requirements and reason about how can I make it do something else for my situation? And will that cause any conflicts or other issues with any of the other requirements?
So thank you. I could not have planted a better question. Thank you very much. We'll talk about the payment for this. No, seriously, that is in many ways the point. So I guess we are moving into the world where all of these systems are personable. So I would like to be able to separate, required and personable. I would like every person to be able to specify their personal preferences. And then I would like to say, well, maybe you're asking too much. This is infeasible. This cannot happen. And so there is in principle nothing in the setup that should prevent the user from saying, my purpose was to have been, there should have been the help. Why didn't this happen? And use the very same system to see what rules would have prevented it. Okay, there is also nothing in principle, and we're hoping to be able to provide this, to have kind of personalization in the ordering of rules, as well as in the conflict resolution. But again, where I think my main point here is we are moving into the world where these systems cannot be engineered once and for all. So whether we like it or not, we kind of would like humans to tell us what is it that they want, and understand why is it that they didn't get it, or insist that they get it, or whatnot. And so the broad goal is to separate what is required, what is contextualized, what is personal, what is domain specific, and be able for the users to get their own rules to say, you know what, whenever I fall, I just want to be helped, and this rule doesn't apply to me. So at the moment, they would need to open the tool and see the rules and see where this would have happened. Maybe there is a yet a better way of human-computer interaction that uses all of this to do this differently. But the intent is exactly that you can personalize how the system will work for you. And that's one of the reasons why I think all of the using the SLEEC rules per particular node to synthesize them either into a monitor or better yet into some sort of guardrails, because this can be done in every node separately, may just be the way to go. Go ahead.
Hey, so awesome work. Thank you for the nice talk. A big theme of your work is usefulness. And so one of the things I'm wondering about is how expressive your SLEEC DSL language is. If I understand correctly, you reduce it to FOL star, right? So basically I'm wondering, are you able to express any SLEEC requirement in your DSL and therefore FOL star? Or do you think you need to improve it more to be able to express other kinds of requirements?
Right, thank you. So reasoning and expressive power are the two enemies in general. right? And we're all going through the space trying to find just the right, combination. We want to say it all, then we say it, and then we don't know what to do with it. Or we don't say enough, and then we're dealing with expressiveness. So SLEEC, so far, we have been observing that our users were able to say everything they wanted to say, ish. For example, right now, you cannot do an and of two events, or you cannot do some logical combination of measures. And so instead, the users needed to have multiple rules, and surely there's a better way of doing it. It doesn't change expressive power. It just changes a bit in the language. Once we start looking at, for example, uncertainty, and once some of the reasoning becomes probabilistic, we start bumping into issues of reasoning. So right now, once everything is Boolean and time, the logic is expressive enough, but it is, we can provide at least bound answers to all of our sleep situations. The more we want to do, the harder it is to reason, and this combination is an ongoing struggle for the duration of computer science, right? We always want to say more. We think this is about right, modulo priorities, modulo uncertainty. Again, uncertainty starts pushing us away from decidability, so one needs to be careful there. We're teetering on this.
Presumably FOL star is not decidable.
FOL star is not decidable, but it is finitely decidable. So if you can limit yourself to the grounding of a particular of like k number of objects, then it is decidable.
So just as a follow-up to that question, you responded and you said there's this trade-off between expressiveness and reasoning, right? Which I completely agree with. But I feel like your answer actually touched on a third thing and implicitly, which also seems like an important part of your design, which is, you could have just started with FOL star and had kind of a one-to-one encoding of the structure of FOL star in maybe a slightly more accessible language. But you chose not to do that, right? You picked a set of patterns. And so I'm wondering, how you went about that choice, which patterns to include, and also, is there a notion of completeness? Is there a theorem that you can express anything you could in FOL star with the right, maybe duplicating some rules or something like you said, or are there corners that are not expressible?
Amazing questions, both of them. So first of all, in the style of parness and rational design and how to fake it, FOL star was built before SLEEC. And then SLEEC became an application. And it turned out that we could express it very nicely. And we already had, that's why the papers are in the wrong order. We first had a solution.
Sure.
In search of a few problems, then we found the problems and then, started doing stuff with the solution. So we know that SLEEC is embeddable into FOL star. So at the moment, there is absolutely a theorem that every expression you can express in SLEEC as per its language and semantics is translatable into FOL star. That is not true that everything you may ever want to express is expressible in SLEEC.
Right. I was interested in the other theorem. Is everything expressible in FOL star expressible in SLEEC?
No, SLEEC is broader than FOL star at the moment. Let me see. SLEEC is
Narrower.
long night of, you all know what. So SLEEC is a sub-language of FOL star. And that means we keep on pushing on it as long as we don't go outside the FOL star. But the moment we go into uncertainty, we go into probabilities. We're outside FOL star. We definitely want to do that. You need a different math. So yes, we're right now decidable and everything is beautiful, but we cannot express a lot of things which are definitely worth expressing. Yes.
So you mentioned that that there should be like a toolkit available, so that way, like as requirements change over time, users can go in and adapt the requirements. And I'm kind of wondering if that's also something that should be extendable to the domain. Because one of your examples for constant domain knowledge was that if a door is open, then it should stay open until it's closed. But then even like the doors in this room have pneumatic pumps on them, so that way the door closes automatically after like 30 seconds. So as these things are deployed in like a range of domains, are the domains themselves able to be changed and adaptable?
Right, thank you, good question. So right now, absolutely. If you know what you're looking for, mix it in, analyze, you're done. A more serious question I think that you're asking is if we're broadly talking about a language or a method of deploying something in different customized environments, where you're deploying it in this building, which means you know something about the rooms, the doors. You're deploying it in a different building with a different configuration and different rules. If you know what all of this is, the language has no issue with expressing all of this and reasoning subject to those expressions. What is harder to do, this is for requirements or for domains. If this evolves, right? If somebody replaces these doors to the ones that open differently, how and when do you know? And what and when do you update? I don't have a good answer for that. But if you do know, there is no concern in expressing all of this in the language and doing reanalysis. So for example, if you want to know, you're calling a contractor and they say, we're gonna give you a door that requires you to, put a thumb in before it opens. You could, in principle, rerun the what if analysis with this to say, you know what, we actually have some users without thumbs or without being able to lift their arms this far, or I don't know what, and that would create a conflict. So in theory, all of that is available. So same way as you could evolve the system, you could try to evolve the domain and see and do the what if analysis to see if this is going to work for your existing users and their customizations. In principle. Yes.
Since we're talking about evolving requirements, similar to, I guess, following up on Andy's question and what we discussed earlier, I saw sort of concern when I saw your examples about like redundancy as a thing that stakeholders might want to remove. Because if in the future they might imagine evolving requirements, and there are rules like A and B where A implies B. If you remove B, it's fine now. But what if I were to change A later? Maybe B is there because it's a guardrail such that even if I evolve A, I want that thing to remain.
We really should do the tag team. So there is a reason why they were called unintended redundancies.
Okay.
Some of the redundancies are absolutely intended.
Okay.
And we find them and somebody says, no, that's an intended redundancy, that's fine, keep it.
But how do they know?
We tell them and then they need to determine. I'm sorry, we can only provide we can only do the, undo, redo, what is the relevant part, etc. We cannot figure out what is intended in the future until it is said somehow. If they would have told us that that is what would happen, we could do the what if analysis, that this could have been redundant there, then, etc. But if we don't know, again, this all boils down to intent. If we don't know what was intended, we cannot provide any analysis. Yeah.
So the users sort of reason through this. Yeah. But the people are like really bad at imagining future changes or
Yes.
future evolution, right?
And we cannot help.
Yeah.
What we can do, right, is we can, as we fix these things, we can maintain the epochs, we can unroll, we can say, was there a redundancy that you evolved, put it back, but we cannot help people imagine stuff. And we talked with Insuk a little bit about this, that people are best at imagining things once they see scenarios.
Yeah.
And so the more we can operationalize this, perhaps using LLM for operationalization and scenario building, the more we can do it's a principally different analysis. It's might help with intent generation. Like, ooh, this is not doing what I ever wanted. I just didn't say it right.
Right, so well, we should probably bring the questions session to a close, so Marsha can get to lunch among other things, but thank you so much for your participation.
and for the questions.